In this lesson, we're going to explore how to find where a line intersects with a plane. So far you've learned how to write a vector, parametric, and scalar equations of lines and planes. I hope by now you understand what direction vectors and normal vectors mean, and that you're starting to be able to visualize space not just as a flat surface, but as something you can move through in 3 dimensions. Now we're ready to ask the question that shows up in physics, architecture, engineering, robotics, even in video games. Where does the path meet this surface? That's exactly what the intersection of a line and a plane is all about. Sometimes the line pierces the plane at a single point. Sometimes the line lies entirely on the plane, and sometimes the line doesn't touch the plane at all. It's parallel and flying by without ever meeting it. Today, you're going to learn how to sub the parametric equation of a line into the scalar equation of a plane, solve for the parameter t to find the point of intersection, and interpret our results: 1 point, no solution, or infinite number of solutions. This is where your algebra, geometry, and spatial reasoning all come together. We're not just solving equations, we're learning to predict how objects interact in space. Okay, so we know now that there's 3 possibilities, so let's take a look at them. Those 3 possible cases in 3 space for a line and a plane. Well, the first one is going to be that there's no intersection at all. We've got a plane and a line, and they are never going to meet. They're parallel to each other. The line and the plane are parallel. The next one that I wanted you to think about is actually number 3 on your page, that there's infinite number of intersections. The line is on the plane. It is everywhere on the plane. It is not just a single point or not touching it. And the third one, well, really number 2 on your page, is that there's a single point of intersection. And this is the one where the line goes through the plane. So single point of intersection, the line goes through the plane. Like a toothpick stabbing through a very thinly sliced piece of cheese, if you wanted to think of it that way. So if we were to draw normals to all of these, if we were to take a look at this, we can see that here would be our normal here, perpendicular. And if we were to use our equation, we'd have our normal dot our direction vector will be equal to 0. That's what makes it perpendicular. Same thing down here. If I were to draw my normal vector, again, we would get n dot d would also be equal to 0 because they're perpendicular. In both of those cases, they're perpendicular. But if we go back and take a look at a single point of intersection, in this case, since they are not perpendicular, we aren't going to have that normal perpendicular to both the line and the plane, then we could say that our normal vector dotted with our direction vector then will not equal 0. And this is our clue to what might be happening. So if we take our dot product and we get it equal to 0, that means that the normal and the direction vector, the line on the plane, are perpendicular. They're perpendicular. Oh my goodness, perpendicular. If we end up that they are not equal to 0, that's where we're going to end up with 1 point of intersection. So if we want to actually solve for this, put some math behind it to see what's going on, it actually is really nice. It is the same procedure every single time. You're going to substitute the parametric form of the equation of the line into the plane. Now, the only extra piece of work that you might have to do here is that if you're given the vector equation of the line, you're going to need to convert it to the parametric form. So this is really just the same thing as finding the point of intersection of 2 different equations or 2 different lines from grade 10. You've seen this before. It's just a slightly different method. So let's find the point of intersection of the line XYZ that has a position vector or point of 3, 2, -1, and a direction vector of 4, 3, 2 with the scalar equation of the plane x minus y minus 2z equals 0. So remember I said the first thing that we need to do here is write the equation of the line in parametric form. So I'm just going to say equation of line in parametric form. And that is just going to be saying I'm taking x, I'm breaking out the x, y, and z components. So x is equal to 3 plus 4t. Y is equal to 2 plus 3t, right there. And z is going to be equal to -1 plus 2t. So now that we've done that, we're going to take that and we're going to sub those values for x, y, and z. So sub the values into the scalar equation. So into the equation of the plane, and solve for that parameter t, because it's that parameter t that is going to be what tells us what of those three scenarios is happening. So we have our equation x minus y minus 2z equals 0, and I'm just going to do a straight substitution. So we have 3 plus 4t is our x value, minus 2 plus 3t, that's our y value, minus 2 times -1 plus 2t equals 0. That's our z value. We'll do some math here, so we end up with 3 plus 4t minus 2 minus 3t plus 2 minus 4t equals 0. We're going to collect like terms, and we end up with 3 minus 3t equals 0. And if we solve for t, then t is going to equal 1. So if t is equal to a number, then there is a point of intersection. So we can take that t equals 1 now and sub it back into the parametric equation to get the x, y, and z components of that point of intersection. So x is equal to 3 plus 4 times 1. Well, that gives me 7. Y is equal to 2 plus 3 times 1. That gives me 5. And z is equal to -1 plus 2 times 1, and that's equal to 1. So this is telling me that my point of intersection between this line and this plane is going to be at 7, 5, 1. Let's do another one. It is the exact same process. Turn the vector equation of the line into the parametric equation, sub into the equation of the plane and solve for t, and depending on what's happening with t, we're going to use that value of t to solve if there is a point of intersection. So we have the equation of the line, xyz is equal to 2, -5, 6, that's our point or position vector, plus t times 3, 1, 8, that's our direction vector, and we have the plane 5x plus y minus 2z plus 2 equals 0. So let's break the equation of the line down into our parametric components. So x will be equal to 2 plus 3t, y is equal to -5 plus t, and z is equal to 6 plus 8t. Now we're going to sub that in to our equation. So we get 5 times, so the equation of the plane. So we get 5 times 2 plus 3t plus -5 plus t minus 2 times 6 plus 8t plus 2 equals 0. We're going to expand, we're going to simplify. So we get 10 plus 15t minus 5 plus t, t, not 6t, minus 12 minus 16t plus 2 equals 0. Collect like terms, and we end up with -5 plus 0t equals 0. So 0t equals 0 when we rearrange, 0t equals 5. So 0t is equal to 5 when we rearrange to solve. So when can 0 be equal to 5? Well, never. 0 can never be equal to 5. 0t's can never be equal to 5. Therefore, there is no solution here. And remember I said at the beginning, if there is no solution, then there's no intersection point and the line must be parallel to that plane. So no 0t equals 5. There's no solution. So therefore, it must be parallel to the plane. So here's another way that we could show that solution, or that there is really no solution from example 2. So if we use our dot product and we get that the dot product of the normal dotted with the direction vector equals 0, and we have the situation where we've already tested to know that the point does not lie on the plane, that would mean that the normal and the direction vector are perpendicular. So there's no single point of intersection. So let's try it. If we took our 3, 1, 8 and dotted that with 5, 1, negative 2 from our line and our point, or line in our plane, that will actually equal 0 if you do the dot product of that. And this is going to tell us that it's either going to be parallel. So this could be parallel, which means there's no solution. There's no place where this line and this plane are going to interact because the line and the normal are perpendicular to each other. Or it could tell us that they're coincident, meaning that the line shares all of its points. There's infinite solutions with the plane. So this one would be infinite. Okay, so if we've done the dot product and we've gotten 0, now we know it's either parallel or coincident. How do we know which one? Well, we're going to sub the point, and we're going to just use the point from the question, which was 2, negative 5, 6. And if we just pop back over here, 2, 5, negative 6 was this point on the line. We knew that that point was on the line. So we're going to use that point. Let's get that back. Sorry if you're watching that and thinking, what is she doing? Okay, so we're going to sub that point, 2, negative 5, 6, into our equation for the line. For the plane, we're going to sub it into the equation of the plane. So just as a reminder, our equation of the plane was 5x plus y minus 2z plus 2 equals 0. So let's sub in this point and let's see if this works out. So we have 5 times 2 plus 1 times negative 5 minus 2 times 6 plus 2 equals 0. Let's figure out what this left side equals. Well, our left side is equal to negative 5. And negative 5 does not equal the right side, which is 0. So the point does not fit on the plane. The normal and the direction vector are perpendicular, but the point is not on the line. That tells us that there has to be no solution. If we ended up with the left side of the equation equaling 0, then that means the point is on the line, and there would be an infinite number of solutions. So if you solve and you get 0t equals 0, then you can conclude that there are infinite solutions. And the line is on the plane. So the line would be on the plane. So remember, you have 3 choices, and I'm just going to summarize them here. So 3 choices with what could be happening with a line and a plane. If our parameter t is equal to some number, then we're going to sub to get the point of intersection, because there will be a point of intersection if t gives us a value. If 0t equals a number, then there's no solutions. This can't possibly happen because the line is parallel to the plane. They are never going to meet. Now, the last scenario, the one we just looked at, that was 0t equals 0, that means there's an infinite number of solutions. And that just means that the line is on the plane. So the line is on the plane. Okay, so it's repetitive. It's a repetitive process for this. I did promise you that this wasn't going to be as mentally challenging as what we've been doing. Conceptually, this is a little bit easier to wrap our heads around. I've given you, oh, there we go. What's happening? Oh, I'm not sure what's happening, why that keeps, I can't get back to it. Okay, hold on, just 1 second. Technical difficulties, shouldn't surprise anybody. Okay, so I've given you page 479, numbers 1 to 5. There's lots of parts to each question. There's lots of things you need to do, but it's the same procedure over and over again. So I really just want you to do as many as you need to feel comfortable with this concept to make sure that you understand it. As always, if you have any questions, feel free to send me an email.